Let's consider some other properties of continuity. This is the definition of the fact that a function is continuous at a point set 0. And using the properties of limits that we have shown you before, is rather easy to see the following. If f of z is continuous at set 0 and capital F of z is continuous at set 0, then the sum of these functions are also continuous at set 0. The product is continuous at that point, and the relation between f of z and capital F of z is continuous at set 0, provided that capital F of z is different from 0 at that point. Let's now turn to the definition of differentiability. Let now set 0 be an interior point in the domain of definition to f of z. We say that f of z is differentiable at the point set 0 if the following limit exists. If this limit exists, we have some fraction of f of z minus f of z 0 divided to z minus z 0, and when z 0 goes to 0, this limit should exist. If it exists, then it's called the derivative of f at the point z 0. It's maybe more common for you to see this symbol delta z instead of z minus z 0. If we use this notation instead, then this definition turns into this definition. F, the derivative of f at point z 0, is equal to the lim f of z plus delta z minus f of z 0 over z 0 as delta z goes to 0. Let's take an example of this. Let f of z be equal to the square of z, and let's now first compute this limit that we showed you above, where we're using the delta z definition. F of z plus delta z minus f of z over delta z. So what is this? Well, we know what f of z is equal to. It is z square. So then we have to replace z with z plus delta z. And here we replace z with z 0. Then we arrive at this expression. So now we are squaring the sum of z 0 and delta z and obtain these three terms. And now we see that this term and this term is equal with opposite signs, so we can remove them, and we are left with these two terms in the numerator. So when we are dividing with delta z, we obtain 2z0 plus delta z, and when delta z goes to 0, we see that this will approach 2z0. So this means that the derivative of f at the point z0 is 2 times z0. So this is does not come as a surprise, because we know when we have in the real case, when we have f of x equal to x squared, the derivative of this is equal to 2x. So it's not a surprise for us that when in the complex case we have a similar result. Now take another example. Recall that in this example that the following: if we call f of z equal to z over the conjugate of z, then the limit f of z as z goes to 0 does not exist, and this we have proven earlier. The same happens for the function g of z equal to the conjugate of z over z. It's exactly the same arguments which we use in order to show that this limit does not exist when z goes to 0. So, with this in mind, consider the following example. F of z is equal to the absolute value of z square. In this case, in order to show this, we must show that the limit in the definition of the derivative is does not exist, that the limit does not exist. So f of z plus delta z, what is that? Well, we replace z by this guy and get this guy. And we should take minus f of z, and f of z is equal to z0, the absolute value of this square. Delta z, we don't change it. And now recall the following, that the square of the absolute value of a complex number is always equal to the complex number multiplied with the conjugate of this number. We have shown you this before. So why don't we replace this? This is a trick actually, but we replace this by this expression. The same for z0 square, the absolute value of z0 square. And this is to utilize this property of this function. And this will be used in order to show that the limit does not exist for the derivative. So we recall that the conjugate of a sum is equal to the sum of the conjugates. And this we have utilized here. And when we are taking this product, we obtain the following. It's very easy for us to obtain this, and we now see that this product is equal to this product with the opposite sign, so we can remove it, and then we obtain these three terms. And we see now that this term divided to z0 equals to this. This term divided to delta z is just equal to z0. And this term divided to delta z is just the conjugate of delta z, which approaches 0 when delta z goes to 0. So this term is actually a constant, and this term approaches 0. So we only need to investigate this first term. What does this convert to when delta z goes to 0? And it does not convert to anything, because this limit does not exist, as we have proven earlier. So this means that the derivative of f in the point z0 does not exist for any set 0 different from 0. You see that when set 0 is equal to 0, then this term will be identically equal to 0 for any value of delta set. So in that case, this limit in fact exists.